All right, welcome to Weather Lab 13, and we're going to be working on lab about hurricanes, and we're going to start with just a little bit of notes on the introduction. So looking down at the intro section of the first page, tropical cyclones are known as violent storms, and they're characterized by one, low pressure, high winds, heavy rain, and rough seas. They form over tropical oceans, and they're fueled by the evaporation of water. So this is the act of the latent heat process occurring and the convection of thermal energy into kinetic. So we're turning in the latent heat process, we have a warming process occurring. So we're taking the warm seawater, which has a sea surface temperature of about 80 degrees Fahrenheit. We're doing latent heat on this activity, so that's the thermal energy. And this thermal energy is going to build up and allow for the air moving from high to low pressures within the storm system. And we're going to have updrafts and downdrafts, and those are going to be our kinetic energies in our system. And so keeping all these things in mind, we're going to look at question 1, and then we're going to move on to questions 2, 3, 4, which are going to look a little bit more at these intro facts. So question 1, draw a surface wind around the eye of the northern hemisphere hurricane depicted in figure 13.1. So for this one, they're just asking, do you remember facts about things? So cyclones in the northern hemisphere have the air moving from high to low pressure, and since the cyclone is the low pressure, that means the air will be moving in towards the storm. So the air is going to go towards the low, right? High to low. And then it's going to also curve because it's going to come under the Coriolis effect. And in the northern hemisphere, when we get a rotation that's going to act, it's going to move in a counterclockwise motion. So around a low pressure center, it moves counterclockwise. And so to draw in our arrows to give us our little depiction, you want to go opposite the clock and in towards the low pressure. So something along this, where we're curving in, but opposite the clock, right? Counterclockwise in our motion. So question 1, pretty easy, and we're all set. Question 2, now we're going to be looking at the image above in 13.2, and we're going to talk about what's going on in this image. And so once again, as a review, this center area here, this is the eye of the storm, and this is the lowest pressure. So this is the lowest low, and this is the eye, right, in our storm. The eye wall, which is the areas right next to it, which I'm highlighting in the yellow, are the areas with the highest wind speeds, and that's because the stuff that's moving into the low pressure will rise before it ever reaches this center low pressure. So these are our areas where air is rising up in the eye wall, and it's also moving at really, really fast wind speeds of 75 miles per hour or more. There's also areas where the air will be having downdrafts and subside. These subsidence zones are called rain-free zones, and so they're here in the highlighted black. There's also other areas of updraft, so it's not just in the eye wall. There's also these rain bands that are areas of updraft, right? So we have these areas of updraft, and this is because this is a big complex spinning system, and so we're going to have areas where pressure will be higher and pressure will be lower. And when you have something that is 500 miles across, 250 miles in radius, it's going to have a complex inner anatomy or complex inner workings for the storm. So how does subsidence at the storm's peripheries make the surface air relatively dry? Well, we're looking at the system here. How does these rain-free zones happen? Mainly because you have downdrafts. Pretty easy question. They're just asking, how do we get rain-free zones? Well, rain-free zones have downdrafts. That's what's happening. In the downdraft, if the air is sinking, can't form a cloud. So rain-free zones are downdrafts. Downdrafts can't form clouds. Therefore, cloud-free. No wetness. Dry, right? So that's question 2. Nice and easy. Question 3, hurricanes gain their energy through evaporation of warm ocean waters. How does the subsidence of dry air affect evaporation rates? How does wind speed affect evaporation rates? So, if the air is sliding down, I'm going to use the picture again. If the air is sliding down, right, and it's picking up Once it hits the ground, it's going to radiate out in multiple directions, right? So it's going to come down out of these little rain-free zones, and it's going to move out and down. What will that do with the air that's currently in this location? Well, it's going to push it out of the way. So it's going to push the air in the updrafts up even more rapidly. So what's going on is this act of the downdraft is aiding the speed with which the air in the updraft will be pushed up, because it's going to push it up and out of the way. It's going to push down and push the air in the updraft and the rain bands up and out of the way. So some sentence that explains that would be great for question 3. So question 4, how do sea surface temperatures affect evaporation rates? What could cause the variation in sea surface temperature ahead of a hurricane's path? So some of this is logic. As far as what could cause differences in sea surface temperature ahead of the path, you gotta use some common sense. There's a lot of things that can cause it. Yearly weather events can cause it. Was there a previous storm? Has an easterly wave formed, right? How's the ocean currents circulating? Are they circulating as normal, or is the ocean current system, like the Gulf Stream, working a little slower this year? So there's lots of different things that can happen. How many days has there been direct sunlight hitting the ocean surface? How has it been cloudy? Has it been not cloudy, not rainy? Is there a lot of air motion? Is the high pressure, surface high pressures where they need to be to the north, or are they over the southern hemisphere? So you can pick a whole lot of things. You could pick things about the Hadley and Farrell cell to explain what's going on in ocean temperatures. You can pick things about ocean currents. You can pick things about the amount of sunlight per day, and pick a couple examples and write about them. Tell me how these things will affect ocean temperatures. And you got so much to choose from. I named so many things right there. Pick like 2 or 3. Write some complete sentences. So that's question 4. And now I'm going to create some notes for Hurricane Hugo before we move forward and answer questions 5 and 6 and so on. All right, so for notes on Hurricane Hugo, first off, the hurricane's name is Hugo. It started out as a cluster of thunderstorms, so that means it was an easterly wave made a bunch of thunderstorm clouds. That easterly wave was located off the west coast of Africa. The storm itself developed September 9th of 1989. It took 2 weeks for it to develop into a hurricane-strength storm. It hit the lower parts of the islands of Guadeloupe, the U.S. Virgin Islands, and Puerto Rico. And as far as the damage it caused, it did create 86 deaths. There was a storm surge of a 20-foot height, so those are the waves that came inland as they were crashing along the shores as the hurricane came over these islands. The winds contributed to high damage, and those severe winds created about 9 billion in damage for the storm. Also make note of its traveling path in the figure of 13.3. Before we move on, just notice that on the bottom of the page, because you might want to go back and reference it to answer the questions. So now let's look at the figures for 5. Question 5, on the figure, draw an arrow to show the forward movement of the storms perpendicular to the coast. And so I'm going to zoom in on that. All right, so now this brings us to the forward motion of a storm. So when we have a rotation of air, the forward motion hits frictional force, and because of that frictional force, it's going to slow the storm down. You can think of a Ferris wheel, and the top of the Ferris wheel being the point of frictional force, or the point where gravity is going to act to pull it down fastest. And so as it rotates around, it's going to slow down, and then when it finally stops its resistance, it's going to pull round really fast. And so we're going to look at these wind speeds and clock them out. So these are in knots. So 2 flags, like this one, means that it's moving at 50 knots and then 50 knots again. So this is 100 knots, right? Over here on this one We have 50 knots, 50 knots, and then 10, 20, 30. So 50, 100, 30. So this is 130 knots. Over here, I have 50, 50, and 10. So this is 110 knots. And over here, I have 50 and 10, 10, and 5. So 50, 60, 75. 75 knots. So that means that when this storm is flowing, it's going to slow down and then pick up speed. And often the fastest part of the storm is to the southern and eastern end of the storm typically. So once again, just drawing up a compass: north, south. This is my west side and my east side, right? East, west. That means that it's going to slow down when I'm going to move around the corner. So this storm, because they want you to draw an arrow for question 5, is going to be slowing down right before it begins to pick up speed again, which means that it's coming inland at this direction. Does everybody see this? Because that's what's happening, is that the speed of the storm, as it rotates around this point at these different stations, it's slowing down, and then like the frictional force gives, and it's going to come around the curve. So it's rotating around, rotating around, rotating around, rotating around, rotating around. Slow down, slow down, slow down, slow down, slow down. Woo! So that's the speed, right? Rotating around, rotating around, rotating around. Frictional, 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 frictional. So that's going to slow the wind speed in this area. Whee! And I'm going to pick up the wind speed. So we can see the wind speed picking up, and we can see where there's very little frictional force around this point here. So that's how we're going to just draw an arrow for question 5, but I want you to fully understand why the arrow would be in that location. How might the forward movement of the storm influence wind speeds within the storm as depicted in the 4 locations? So we've already kind of answered this. Just talked about all these wind speeds and frictional force and why one particular station is slower than the other. If you would like to help identify your stations, you're welcome to label them. So you do this right on your lab. You can name them, say like this is point A, point B, point C, point D. You do not have to use letters. You can name them anything and use them as a reference to help answer or write a sentence to answer 6. But we just answered this question, going through these different knots, wind speeds, and why A is slower, B is a little faster, C is so fast, and D is beginning to slow down again.